transcribing the lecture. So let's try not to say anything crazy because it is being recorded. I know how we can talk about some crazy stuff in this class sometimes, so we're going to try to keep that at a minimum. And then the other announcement that needs to be made is that we were supposed to have an exam today, I think, right? But since we're not in class, I have moved the exam to Thursday, assuming we come back on Thursday, because I still don't know what's happening. And so instead of doing the exam today, we'll just go over the first part of the chemical elements lecture, which will be, I think, I don't remember how many slides are. Let me look real quick. There are 45 slides, so about 20 slides today is what we'll do, and we'll start that today, and then we'll have our exam on Thursday for last week, or that was supposed to be today, and then we'll continue on with the chemical elements lecture next week. Does anybody have any questions about that? If anything, it gives you 2 extra days to study for the exam, right? Happy about that, right? All right. So let me go ahead and share my screen, and we can start this bad boy off here. Let me see if this is going to work here. Let's see. Let's see here. Share. There we go. And then maximize. Like that. And then this. And then what we'll do is start the presentation, I think. And then switch like that. Like that. All right. So I have the chat open. So if you have any questions, you can either ask through the chat, or you can ask by unmuting yourself and asking through your microphone, right? All right. So today we're going to start chemical lectures. Like I said, it'll be pretty short. I'm going to try to get through like maybe 20 slides, and that's about it. And we'll do the rest of it next week, because Thursday you'll have your exam. And that's all she wrote, right? So let me make sure I can write on here. Today I will use purple. Purple will be the color today. Okay, so let's take a look at the learning objectives, right? Today we're going to try to identify and describe what chemistry is, what its major divisions are. Identify and describe matter, pure substances and mixtures. Describe liquids and solutions and their types. Describe solubilities, solids, and gases. Describe discovery and occurrence of elements. Describe atoms, molecules, and allotropes. And we'll probably stop it right there. So this will be for today right here. Right? And then next week we'll do the periodic table and its organization, valence electrons, periodic trends, and describe how to name compounds, right? So this stuff will be next week. Okay. So what is chemistry? Well, chemistry is a division of physical sciences. We talked about that before. One of the physical sciences. And so really the definition of chemistry is the study of matter, right? The study of matter and how matter interacts with each other, right? And so chemistry has been around for a very long time. The Egyptians practiced chemistry, the Chinese, Mesopotamians. And how did they do that? They did that by making wine, and they're working with metals, dyes, glass, pottery, embalming as early as 3500 BC. Wow, that's a long time ago, right? That is a long time ago. And so if I'm going too fast and you can't write everything down, don't worry, because like I said, this one is being recorded, so and you'll have access to the recording. All right, so before chemistry was actually called alchemy, right? And alchemy was all about trying to turn things into gold, right? Like King Midas type of thing, and also finding the elixir of life, right? Finding the elixir of life. So modern chemistry didn't actually begin until 1774, right before the American Revolution, by a French guy named Antoine Lavoisier, right? It's not Lavoisier, it's Lavoisier, okay? Antoine Lavoisier, right? And he used chemical methods or used quantitative methods, right, to avoid things like superstition and secrecy and mysticism. We don't like those things, right? We don't like mysticism. We don't like superstition. We don't like secrecy. Okay. Nisha Hinton declined. You declined? Who? What? You're already in the class. How could you decline? What's happening here? Anyway. So what are the 5 major divisions of chemistry? We have physical chemistry, which mainly deals with the chemistry of like physics and stuff like that, like the Higgs boson and nuclear stuff, nuclear chemistry, that kind of, that's all physical chemistry, right? Quantum mechanics, that's all physical chemistry. Everybody's heard of quantum mechanics. I talked about that during atomic physics, last week, right? There's also analytical chemistry. That's the chemistry that I do, right? And what we do in analytical chemistry is we identify what something is and how much there is in there, right? Which is actually very helpful when you're a forensic scientist because you're trying to bust people for drugs, I guess. So you have to know how much cocaine there is and how much cocaine there is. Wait, you have to know what the powder is, whether the powder is cocaine, and then also know how much cocaine there is because the amount you have can either give you a misdemeanor possession charge and or a intent to distribute charge or a trafficking charge, right? And trafficking is bad, so don't do it. Don't traffic cocaine. That's bad for you. Okay. There's organic chemistry that deals with mostly carbon compounds, right? Not to be confused with organic, charcoal or, excuse me, what other stuff there is? There's a crap ton of organic things, right, that you can buy at the supermarket, but at the store these days, right? But don't confuse that with organic chemistry. Those are 2 different things. There's inorganic chemistry that deals with everything else, right? That's not carbon chemistry. And then there's biochemistry, which is about the chemistry of life, and so that's my other specialty. The chemistry of life is my other is the other chemistry that I study. I'm trying to get people. I'm getting emails from people saying something here. 1 second here. People in the class. What's happening? Peter, I just got an email from you. Why are you sending me why are you sending me an email in the middle of class? What's happening here? You're already in class. Why are you sending an email? All right, so let's keep on rolling here. Oh, there we go. So which of the following is not a discipline of chemistry? Oh, I forgot something. So some of you might be on your phone, so you might not be able to scan this barcode. So let me get the what's it called? The link for you real quick. 1 second. Are any of you using your phones to watch this? If nobody's using their phone to watch this, then I'm not even going to bother. Of course, it's Win. Win's going to say that he's using his phone. He's going to be the problem child here. Yep, he's the. Okay, Win. Give me 1 second. I'll. Oh no, there are a few more people, I guess. So. Okay, it's not just you, Win. It's not just you. Okay, I won't just blame you now. All right, give me 1 second. Let me get the link out so you can. I'll put it into the chat so you can answer using the link. 1 second. Let's see here. Search chemistry. That must be it. Yes, this is it. Collect responses. Okay. Here is the link for the question. Go ahead and go ahead and answer it through that link if you are on your phone. And then if we have any other questions come up, I might just skip them because it's kind of a pain having to do this. But so make sure you're here for your attendance. Okay, make sure you're here for your attendance for this question. All right, so I'll go ahead and switch back to the PowerPoint. Okay, Wayne is typing something. Can I see the answers? Oh, that's right. 1 second. I'm still trying to get there. And then switch display settings. There we go. Now everybody should see the answer choices. I think we finally got this working now. Oh, sorry about that. Didn't mean to do that. There we go. Okay. All right. I think I got everything back together again. Sorry. Haven't done this in a while. Virtual teaching. Let's see here. Turn on the pen again. I think I was using purple, wasn't I? Yeah, I was using purple. All right. Okay, so the question says, which of the following is not a discipline of chemistry? Is it analytical chemistry? Is it organic chemistry, biochemistry, or geology? Right? Or geology. And if you haven't answered yet, I'll go ahead and tell you the answer. It is what? No, I'm just kidding. What does everybody think? What's the answer? Everybody answer in the chat. Everybody, well, the people who have answered to say D, that is correct. The answer is indeed D. Good job. Good job. It is indeed D. Remember what I call geology. Don't tell anybody this, but geology is like the younger brother of chemistry. So I don't know why geology is considered, a physical science when it's just like the under thing. So just the under thing. Let's see here. Okay. Let's make sure I'm back on track. I think I am back on track. All right. So let's keep on going then. Oh, dang it. What happened here? 1 second. There we go. All right. So what is matter then? Because remember, chemistry is the study of matter, right? So what is matter? Well, matter is anything that has mass and takes up space, right? And it can either be one compound or a combination of chemicals, right? And so there are 88 naturally occurring elements that comprise virtually all of matter. Okay? So if you remember back when we were talking about nuclear physics, and I told you that there's these things called the transuranium ones, right? Transuranium is 92 because uranium is 92. So anything after that is man-made, no longer natural, right? But even of the 92 that are natural, only 88 actually comprise everything around us, right? Excuse me. Their chemical and physical properties affect us continuously, and then again, I already said this, but matter is anything that has mass, takes up space, and so we classify matter as either pure substances or mixtures, right? And so if you're a pure substance, you're either an element or a compound, or if you're a mixture, you're either a homogeneous mixture or a heterogeneous mixture. And we'll talk about what those are in a second. If you don't already know, solid is a state of matter, liquid is a state of matter, gas is a state of matter. And then if you shoot some electricity through a gas, you can get plasma, which is also a state of matter, right? Also a state of matter. So let's talk about pure substances, right? What are pure substances? Pure substance is a type of matter where all the samples are the same, right? Same composition, same identical properties, right? So either you have all the same elements or you have all the same compound, right? And you are a pure substance, okay? So for example, right, tin is an element, and it's a pure compound, or sorry, pure substance. Sulfur, the yellow powder that smells like, butt, right? It smells. If you ever watch Supernatural, right, the show Supernatural, then whenever they smell sulfur, they always think of, they always know that there's a demon coming, right? Is it demons that do sulfur? I think so. If you know about supernatural stuff, and I'm right that the smell of sulfur indicates there's a demon, let me know, because I don't remember. I'm pretty sure it's right, but just let me know anyway. Answer in the chat, okay? Anyway, sulfur. Diamond is also a pure substance, right? Because it's made of carbon atoms, all carbon atoms, right? We also have pure compounds, right? Like sugar, water, and baking soda. Those are multiple atoms, like put into one molecule, right? Like a molecule of water, molecule of sugar, molecule of baking soda, right? But then when they get together, they're all the same molecule, right? Salt, too. Proteins, right? Copper sulfate. Those are all pure substances. They don't have any other compound in them, okay? They don't have any other compound in them. And so no one's answering my question about supernatural sulfur. Does none of you guys watch TV? What's going on here? Like, nobody watches TV? I guess that's not a thing people do anymore. Right. Supernatural's a fun show. Yes, they also leave a trail of sulfur. Thank you, Alyssa. Thank you. Thank you, somebody, for watching TV. Okay? So, it's the golden age of television. You should be watching more TV. Anyway. All right, so what is a mixture then, right? What is a mixture? A mixture is exactly what it sounds like. It's a mix of different compounds, right, together. So there's a homogeneous mixture where if you look at it, it looks all the same, right? And there's also a heterogeneous mixture. When you look at it, it looks all different. So what are some examples? Well, for a homogeneous mixture, right, things like vodka, that's a homogeneous mixture. Why is that a homogeneous mixture? Well, because you have alcohol and water mixed together, and you can't tell the difference between the alcohol and the water, right? Steel, that's a homogeneous mixture because you look at steel and it's just metal, right? You don't know that it's a mixture of like carbon and iron and all kinds of other stuff in there, right? Other metals. Rainwater, also a homogeneous mixture, because if you were to collect rainwater, it looks just like water, but you wouldn't know that there's other things in that water, right? And air, there's also a homogeneous mixture, right? Another homogeneous mixture. What are heterogeneous mixtures? A bowl of cereal and milk. Wait, that doesn't make sense. Bowl of cereal and milk. Cereal in a bowl in milk. No, wait. Cereal and milk in a bowl. There we go. Right? You can see the cereal and the milk, and you can see the milk. So that's how you know it's a heterogeneous mixture, right? Ice and soda, also heterogeneous mixture. Blood, heterogeneous mixture. But wait a second, when you look at blood, it just looks red, right? But if you let it sit for a second, you'll see that the white blood cells actually kind of like sink to the bottom, and then you have your plasma and your blood, right? And then soil. Soil is definitely a heterogeneous mixture, right? Because you can see all kinds of stuff in soil, including bugs. So this is how you define what everything is in your life, right? In the universe. First thing is it matter? Of course it is. If it takes up space and has mass, it's matter, right? So the question is it a pure substance or is it a mixture, right? If it's a pure substance, then you know that it's all made of the same stuff, right? Now, is it a pure substance of elements? That's the ones that have all the same atoms. That means same number of protons. Or is it a pure substance of compounds, which has several different elements in a compound, right? But it's also the same compound. On the other hand, is it a mixture? Well, you know it's a mixture because it is a composition of a whole bunch of different things. Is it homogeneous? Well, it's only homogeneous when it's uniform. Like you can't tell the difference. Or it's non-uniform. That's a heterogeneous mixture, right? You can use physical processes to separate out, right, mixtures. How do you do that? It's like using a strainer, right? When you're boiling your macaroni, or boiling your spaghetti pasta or something like that, you have a mixture of water and spaghetti, right? But then when you get a strainer and you pour the water in the spaghetti into the strainer, the spaghetti gets filtered out, right? It's still spaghetti, but it got filtered out, and the water goes through and goes down the drain, right? And so that's a physical process. Being able to go through a process in which you filter something, that's a physical process. Other physical processes are things like condensation, right, or evaporation, or sublimation, things like that, right? Melting, freezing, those are all physical processes. Chemical reactions, on the other hand, they're different because they actually go through and change the thing itself, right? It's not the same anymore. It's not the same anymore. So it's kind of like when you throw, onions onto a frying pan and you fry it up to get some grilled onions for your Coney hot dog, right? Your James Coney Island hot dog, some grilled onions. The onions start to turn brown. Well, why? Because there's sugar in the onions and they're starting to caramelize, and so the sugar is actually changing when it caramelizes, and so that is a chemical process, right? That's a chemical process. So there you go. We had a group that did their experiment on how much carbon dioxide could be made from mixing baking soda with different acids, right? Well, you had baking soda, which is baking soda, and you had the different acids, let's say sulfuric acid. You mix them together, and they made all these fizzing noises, right? The fizzing sounds, and then carbon dioxide was produced, right? So the baking soda got turned into carbon dioxide by the sulfuric acid. So that is a chemical process, right? It's no longer the same anymore. So whenever bubbles happen or burning happens, that's usually a chemical process. All right, I'm just going to skip these questions because I don't want to have to do the link every single time. Okay, so just make sure you answer the first one so that I know that you were here today. Okay. All right. So liquid solutions. There are two parts of a liquid solution. You have the solvent, right, and you have the solute. So the solvent is the thing that you use to dissolve the solute. So for example, if you have salt and you want to dissolve it in water to make salt water, right? The water is the solvent and the solute is the salt, right? Solute is the salt, okay? So the thing to know about this, though, is that water can only hold so much solute, in this case salt. Once you dissolve it, it can only hold about 30 grams of salt, right? If you try to dissolve any more than that, say 40 grams, and you try to dissolve it in water, you'll just end up with some salt left over at the end, right? You've seen this happen before because you'll take things like sugar and you put it into some iced tea, and some of it dissolves, right? But some of it doesn't. It just sits at the bottom, right? And just kind of like, floats around, and you drink it, you get a whole bunch of sugar in your mouth, right? That's because you've met the maximum solubility of that in the tea, right? For sugar. I don't know what that is for sugar, but for salt at least, it's 30 grams maximum solubility, right? So when you have a solution that doesn't have all of the 30 grams in there yet, right, of water, then we call that an unsaturated solution. An unsaturated solution is a solution that still has room to dissolve more salt, right? It doesn't have to be salt. It could be anything. It could be sugar or whatever. But a saturated solution is a solution that has the maximum amount of salt already dissolved in it, or whatever you want to put in the water, right? Maximum amount. So here we have a saturated solution because we have salt left over at the bottom, okay? Those are two words you need to know. Unsaturated and saturated. Saturated means that we have reached the capacity of the water. It will dissolve no more. Whereas unsaturated means it still has room, okay? So how do things dissolve? Well, really what happens is that the water molecules goes in and starts to pick off one of these little atoms, right? These little atoms of salt, okay? Because salt's a crystal. Water will go in and actually break it apart and make it dissolve in the water. That's actually what dissolving means, right? And so there's this thing called dynamic equilibrium that happens. And what that is that when it reaches to a point where there's the same amount of solvent dissolving as there's amount of solvent not dissolving, right? And so, or not dissolving, but like it goes back and forth. But there's it dissolves and it dissolves and undissolves. The word is called precipitate. Undissolves at the same rate. So the net effect is that you have stuff left over at the bottom, right? That's not completely dissolved. Okay, that's not completely dissolved, and that's called dynamic equilibrium. So just remember the words unsaturated solution and saturated solution. Okay. So interestingly enough, as you heat up water, right? As you heat up water, more and more stuff can dissolve into it, right? Here's sugar. So the key to making sugar dissolve in iced tea is to actually put the sugar into the tea while it's still hot, right? Right after you boil the water, or you shouldn't boil water to make tea. It doesn't have to be boiling. It can be like 150, 60 degrees. It doesn't have to be 212. But get it really hot, and you're about to do your tea, your big jug or big pitcher of iced tea, right? Get it really hot, and just get the tea in there. And while it's still hot, you could get in like 2 or 3 cups of sugar in that one pitcher. Back in Alabama, my friend Victoria used to put 2 or 3 cups of sugar into her iced tea, right? And it would never work if the tea was already cold. But she just waited. She just, she brewed that tea hot, and then dumped in the sugar, right? Well, while it was still hot. And I'm not even joking. She could get like 2 or 3 cups of sugar into that tea. It will completely dissolve. And it was like drinking syrup. It was crazy. It was very viscous, right? So I wouldn't recommend doing that. That's like the recipe for diabetes, right? But you can do that, right? Because the hotter the water gets, the more sugar can dissolve, right? The more sugar can dissolve. Okay. The same thing is true of a lot of other elements too, like potassium nitrate, sodium nitrate, sodium bromate, right? That's bromine, right? Potassium bromide, all those salts. Potassium chloride. I think they actually use potassium chloride in like lethal injection. Yeah. So, but yeah, the hotter water is, the more easy things can dissolve in it. Kind of fun. So what you could do is once you've reached the point of saturation for water, you can heat it up, right? And you can add more stuff to it, more salt to it, right? And the cool thing is that once you do that, what you get is called a supersaturated solution, right? And I wish we were in class because I could show you a supersaturated solution in action. It's kind of fun. Because when you get a supersaturated solution going on and the solution is cooled down and all the stuff is dissolved in there still, right? What you can do is you can add a nucleation site, like a new crystal, into the water, and it will cause all of the stuff that's in the water to come out of solution, right? All the salt. What that does is it causes heat, and you can use that as a heating pad and stuff like that, right? And I actually have one of those, and I was going to show it to you in class, but we're not in class, so I can't show it to you. So I'll show it to you the next time we're in class. So what is a supersaturated solution? Excuse me. Choked on my spit there. What's a supersaturated solution? It's a solution at which you've already reached the saturation point, but then you heat it up some more, right? You heat it up and you can add more stuff to it. That's called a supersaturated solution. Excuse me. Choked on my own spit. All right. So gases, they're the opposite. Gases are the opposite. Gases are more soluble in water when it's colder. When it's colder, right? And so that's the reason why when you have a soda and you leave it in the refrigerator, right, it stays cold. Right? It stays cold, of course, in the refrigerator. But a cold soda will also retain its fizziness longer than a warm soda. When you pour that soda into into a glass and leave it out on the counter, it warms up. And then what happens? The soda gets flat. It gets flat because the heat from around the room makes it so that all the CO2 leaves the soda and it's no longer fizzy, right? It's no longer fizzy. So it's completely different. It's the opposite with gases, right? With gases, the colder the water, the more soluble the gases are. Whereas for solids, right, the hotter the water, the more soluble it is. Okay? It's the opposite for gases. It's the opposite for gases. I'm going to skip that. You can answer it if you want to, but I'm going to skip it because I don't want to have to put in the link. Right? So let's talk about discovering different elements. Right? Let's talk about discovering different elements. So in the earliest civilizations, we discovered 12 elements. Right? Gold, silver, lead, copper, tin, iron, carbon, sulfur, antimony, arsenic, bismuth, and mercury. Right? They all 12 are later proven to be elements, right? And then in 1669, we discovered phosphorus in Europe, right? We discovered phosphorus in Europe, okay? After that incident happened, right? After that incident happened, there was this huge, like, uptick in the discovery of elements, right? This huge uptick in the discovery of elements, right? We discovered phosphorus, then we got cobalt and zinc, right? And then by the 1800s, Humphrey Davy, a very prolific chemist, right, came through and gave us some more here: sodium, potassium, magnesium, calcium, barium, and strontium, all those elements, right? And you can see how throughout the years we just keep on going up and up and up and discovering more elements, right? More and more elements. So, and as I said before, about 30 elements have been not discovered but synthesized, right? Synthesized. So the occurrence of elements, I bet you didn't know this, but the human body is 65% oxygen. Can anybody tell me in can someone tell me in the chat? Can someone tell me in the chat where all that oxygen is? Where's all that oxygen that we have in our bodies? Someone tell me in the chat. Yes, you have to participate. Well, don't be so specific, Lana. Be wider, like wider thinking. What is it? Don't use like body parts or anything like that, but just chemically, what is it in? So yes, it is in the blood, in our breath. That's true, but really, it's water, right? The oxygen in our bodies, right, is mostly the water because our bodies are made of 75% water, right? And so the element oxygen, right, is most of what our body is made of, and it's because of water, right? So the oxygen you're talking about is like O2, right? The oxygen that you breathe in, and then your blood vessels take it, and then blood cells take it to the lungs, back and forth, back to your heart, all that kind of stuff. Whereas the element oxygen, though, is not only there, but it's also mostly in water, right? So that's a lot. That's a lot, okay? The Earth's crust also has 47% oxygen. I bet you didn't know that the Earth's crust, most people would think that the Earth's crust is mostly made of iron or something like that, right? So let someone tell me now in the chat, where is most of the Earth's crust? Where in most of the Earth's crust is the oxygen? Like, where's that at? And if you excuse me for just 1 second. Sorry, I had to blow my nose. I didn't want to do it on the thing. Okay, so I mean, I don't mean like what part of the Earth, but like where on the Earth is all the oxygen? Like, think of the things that we have on Earth, right? And where do you think most of the oxygen would be? That's true. In the oceans, you're getting very close. So what it is, it's actually sand, right? The Earth's crust is made of a lot of sand, and sand is made of a compound called silicon dioxide, right? So there's a lot of oxygen in the Earth, not in the form that you would think of, because when we think of oxygen as something we breathe in and breathe out as a gas, but a lot of the oxygen, the element oxygen in the Earth, is actually in sand, right? And so That's where all the Earth that's where all the oxygen is in the Earth's crust, sand and the soil and dirt and stuff like that. It's a lot of it, right? Interestingly enough, the hydrogen is actually the most. Hydrogen is the most common element, right? 75%, which makes sense because hydrogen is a very simple element, and so it's the one that's made that has the most abundance in the universe. Helium too, because it's the second most, right? The second most easiest, right? It's only two protons, right? So these two right here, hydrogen, helium, most abundant in the universe, right? But on Earth though, it's oxygen. It's kind of funny, right? And you'll know this later when we go talk about stars, because stars are made of helium and hydrogen, right? Stars are made of helium and hydrogen. We already know this too, right? Nitrogen is 78% of our atmosphere, and the other 25% or 21% is actually oxygen right there. And so back in the day, though, it wasn't like that. Back in the day, during the Carboniferous period, it was actually CO2 that was mostly in the atmosphere, right? But the plants got together and they breathed in all the CO2 and made oxygen. That's how we can breathe now. Good for us. There was one point where oxygen was actually really high in concentration in the atmosphere. And so, like, way more than even nitrogen. And that was back in the days when we had, like, bugs, like dragonflies that were the size of, like, cars. Can you imagine that? Can you imagine a dragonfly that was the size of a car? Unbelievable. Crazy stuff. But, I mean, that's because there was a lot of oxygen back then. And back then, with a lot of oxygen, you can, build bigger bodies, I guess. Anyway. All right, I'm going to skip that right there, right? So let's talk about atoms. We talked about atoms already before, right? But let's just talk about them in a chemistry sense. Atoms are the individual units of matter, right? The individual units of matter, and they're usually in a repeating pattern, right? In a solid. So here's solid iron, and so each one of these little balls is an iron atom. Okay. And then for gases, like the noble gases, right? There's single atoms that just float around and bounce around inside of a container, right? So here's neon, right? Here's neon. And those individual balls are just atoms of neon floating around, bouncing around very fast, very quickly, right? You shoot electricity through them and you see light. Hydrogen, though, is what we call a diatomic, right? So hydrogen is only happy when there's two of them together, right? A little bit incestuous, but that's okay, right? And so, has anyone been watching the show Loki? You know how Loki fell in love with himself, like not himself, but like his variant himself, right? I'm not spoiling anything, am I? I mean, that was last season. Well, last season, Loki fell in love with himself, right? And so that's like hydrogen. Hydrogen's falling in love with himself, right? A different variant of himself. There are other ones like that too. Like oxygen likes to be with itself too. So does chlorine. Chlorine likes to be with itself, right? What's another one? Nitrogen likes to be with itself. There's a lot of them that like to be with themselves, right? And what do they look like? Well, they're just a pair of atoms of each floating around, bouncing off of things inside of a container. This is hydrogen, though, right? But the other ones look very similar. So let's talk about molecules then. What are molecules? Well, molecules are the combination, right? They're the combination of atoms put together, right? So here's what a hydrogen hydrogen molecule looks like, right? Two H's put together. Here's a water molecule, right? A hydrogen and another hydrogen combined with an oxygen. This is ammonia right here. If you ever use Windex, right? Windex is ammonia. And so Windex is that blue stuff that you spray on glass to wash windows and stuff. That's ammonia. And this is actually called methane, right? Ammonia and methane. Right? And methane is the stuff that comes out of your gas stove, right? That you use to cook with. That's methane, right? So this is just some pictures of some more diatomics right here, right? So we have hydrogen right there, nitrogen, oxygen, diatomic, fluorine, all the ones I showed you before. Oh, I just realized that the name of the thing is down here. I just wrote it twice. Sorry. chlorine, bromine, iodine. They all like to be in pairs with each other, right? They're diatomics. They're in love with each other, right? There are also these things called allotropes. Okay, these things called allotropes, and so allotropes are just different forms of the same thing. For example, carbon, right, which is what a lot of things are made of, especially like us ourselves, right? Carbon can take the shape of a diamond, right? And when it takes the shape of this diamond right here, it's very structured, right? The more structured a diamond is, the more expensive it is, right? The clearer it is, the more clarity, the less color it has, that's a more expensive diamond right there. So that's diamond. Carbon can also be in the form of graphite, right? Graphite. This is carbon in the form of graphite. Does anybody know what graphite is in? Someone tell me in the chat. Hello? Anybody there? Hello? What's in? What's graphite in? Is it like wood? It's something that's made of wood. Something that's made of wood. And here I see some people. I'm here, but I don't know the answer. Thank you, Win. I appreciate you saying something. You're all using, well, not all of you, but some of you are using it to write with right now. I know I don't mean an Apple Pencil, but I mean a pencil, right? Pencil lead is called graphite. It's not made of lead, right? If pencil lead were made of lead, you'd all have, excuse me, you would all have heavy, what's it called? Heavy metal poisoning. There it is, right? Because lead actually is a contributor to heavy metal poisoning, right? And so the pencil lead in your pencil is not actually lead; it's actually made of graphite, right? And if you're using a pencil, you're using graphite. That's what this is in pencils. Oh, I don't even know how to spell pencils. There it goes, in pencils, right? And so you see carbon here, right? And carbon can be made into a diamond, and it can also be made into pencil lead, which looks very different from a diamond, right? Carbon is also what's in coal, right? Or charcoal when you grill something, right? All of that is carbon, but they all look very different. It also can be made into this thing called a buckyball, right? It can be made into this thing called a buckyball, and this buckyball, right, is also made of carbon. But the point of it is that allotropes are all made of the same elements, but they look very different, right? They look very, very different. Diamonds look very different from pencil lead, and they look very different from charcoal or coal, which look very different from a buckyball. That's what an allotrope is, right? Two or more forms of the same element that have different structures, right? In the same physical phase. These are all solid things, by the way. Charcoal is solid, pencil lead is solid, diamonds are solid, buckyballs are also solid, right? But they are very different in physical and chemical properties, or sorry, physical properties, right? Because in their bonding structure, right? But they're still all carbon, right? And that's what makes them an allotrope. It's kind of crazy, right? Makes them an allotrope, which is different from like water, right? Because water, like you have water as ice, or it could be liquid water, or it could be gas, which is water vapor. But that's still all the same water, and it's also just a phase change, right? So they change phases. The crazy thing about carbon is that these are all solid carbon, right? And they're all different, right? All solid water is all ice, no matter what, right? But for carbon, when it's solid, it could be in all kinds of different places or all kinds of different like forms. Well, that's what we call an allotrope, right? That's what we call an allotrope. All right. So here's some allotropes of oxygen too, right? We have oxygen, which is O2, gas. That's what we breathe in. Well, just that part, right? That's carbon dioxide. But when we breathe in, That's oxygen we're breathing in, right? But then we also have ozone, right, which is O3. Ozone is the stuff that's in the ozone layer in the atmosphere that blocks UV light from hitting the Earth's surface, right? And helps prevent you from getting skin cancer. That being said, you should still wear sunscreen, right, when you go outside. Just make sure you don't get skin cancer. It's bad for you. Skin cancer is very bad for you, right? But yes, the ozone layer, up in the ozone layer, is made of ozone, right, is in the atmosphere, and it blocks UV light from hitting the surface. It helps with skin cancer stuff. But so the interesting thing about that, though, is that there's a very big hole that is actually in the ozone layer right now, right? That's actually been put there because of us using molecules down here on Earth uh, that break down the ozone layer, called CFCs, chlorofluorocarbons, right? So things that are things that are chlorofluorocarbons are things like Freon, like the thing that you put into your AC when your car's AC doesn't work as well, right? It's not cold anymore, so you have to fill it with Freon, right? There was a point where you actually had to have a license to buy Freon to put into cars, but nowadays you can just go to AutoZone and get one of those like pressure gauge Freon refiller things that are disposable now, right? But Freon does deplete the atmosphere. The other thing that depletes the atmosphere too is things like hairspray that had CFCs in them, or even like albuterol inhalers. Like if any of you guys have asthma, you have to use a little inhaler, right? And you breathe in. The thing that sprays out the inhaler stuff into your mouth or your throat is a CFC, right? And that caused the holes in the ozone layer. So nowadays they don't use CFCs anymore because CFCs are bad, right? They're bad. So now all your inhalers are called HFAs, right? So now most inhalers have HFAs now in inhalers. And I don't know about you, but HFAs don't work as well as CFCs do. I don't feel like when I use my inhaler, I don't feel like the medicine is going as far. And so, yeah, they should just stuck with CFCs and forget about the ozone layer. No, I'm just kidding. Don't do that. Ozone layer is important, right? So now we use HFAs. So if you have asthma and you have an inhaler at home, you should check to see if it has HFAs or if it has CFCs. If it has CFCs, you're killing the ozone layer, right? But if it has HFAs, then you should be okay. Good job. All right, so I'll just answer this question real quick. Which of the following is not an allotrope of carbon? Right? We know diamond is. We know that graphite is. We know that buckyball is. Definitely the one that's not is Malekith. Malekith is just the dark elf from Thor to the Dark World. So yeah, I made that up. Well, I didn't make it up because it's a dark elf's name. But anyway. All right, so I think that's going to be it for today. I want to start talking about the periodic table next week, and so we'll continue this next week. Does anybody have any questions? If not, just remember your exam is on Thursday now. Okay, your exam is on Thursday, and we still have lab on Thursday, assuming that we can come back to school. All right. So, any questions? If not, have a good week. Thank you. Bye-bye. Thank you. Bye-bye. Oh, thank you. Thank you for coming today.